now these are the two disadvantages of the Bezier, so to speak, the global change, because when you change one control point, the entire curve changes and the degree is closely associated with the number of control points. Okay, these two are the problematic things we saw in Bezier. So the B spline actually goes one step further and then eliminates these disadvantages, and naturally you can see that they are going to be a little tricky on that. Okay, now these are all some sentences and I don't know whether we'll have the meaningful of all these sentences. Okay, one thing is that like the Bezier curve is like a single piece curve. So if you draw a control point, this is a single piece curve. Okay, whereas in Bezier in general, what it may happen is that there may be one piece for one guy, okay, something like this, and then maybe another piece for another guy, something like this. So B spline is basically a piecewise curves joined with certain kind of conditions. We don't go into how these are joined. Okay, so what happens is that we will start numbering from B1, B2, not from B0, so we will start from B1 to B4. So this amounts to n plus 1 in terms of terminology, but you can see it's still n number of control points. It's just a little bit terminology difference to account for the equation. Okay, and then there is one more factor that is going to come into picture, which is called order k. Okay, so in the Bezier, we always saw that if there's 4 control points, then the degree is 3, because 0, 1, 2, 3 guy, and we always know that degree guy is 3. There's no way you can find a degree guy 2, even though it's a straight line. Okay, remember, even though you may get into a straight line, but still the degree of the straight line is not 1. Okay, it's more than 1 even in Bezier. Whereas here we will have more control on the order. Order is basically one above the degree. If n is the degree, then the order is, sorry, if order 2 means, then you have a degree 1 curve. Okay, so like if k equal to 2, then the degree of the curve is 1. Okay, degree is 1. So you have to remember that. When k equals 3, then you have a quadratic curve and so on. Okay, now you remember that this is not one piece, it is a multiple pieces. I'll tell you how it is multiple pieces. I'll give you a geometric feel for this. And the order can vary from 2 to n plus 1. That means what? If I have k equals 2, then that means what is the degree of the curve? Yes.
2, sir.
What will be the degree of the output curve if k equals 2? All are sleeping.
1, 1. Sir, 1.
You see, that is what I told here, right? When k equals 2 or k means the degree is less, 1 less than k. Okay, if k equals 2, I mean I'm going to get a single degree curve or a degree 1 curve. Okay, and there is one more thing called as knot vector. So obviously you can see it is heavily involved. So I won't be able to explain in all things great detail, but I'll try to do as much of as much as possible. In B spline is really a challenging topic for I would say teacher on that. Okay, so I'll start with the convex hull property, which is I think gives a much more intuitive feel of the equation. Okay, that is why remember I keep insisting on the convex hull on it. Okay, now this is the input set of control points. Okay, now with k equals 2. K equals 2 means what is the degree?
1, sir.
Degree 1. Okay, now how the curve will look in case of Bezier. So if you draw a Bezier curve, right, for this guy, then it follows the shape like something like this. Remember, it never goes out of shape, something like this maybe. Maybe something like this. Okay, this is how the Bezier curve will look. What will be the degree of this Bezier curve? How many points?
Should be 1. Oh, sorry.
8, sir. 8, sir.
Okay, degree of Bezier curve is very high. Okay, now
yes,
remember we are taking in something called k equal to 2. That means you are going to get a B spline curve of what?
Of degree 1.
Of degree 1. Okay, how does it happen? Okay, this is very fascinating, isn't it? Now what happens is that, you remember in the case of Bezier, the curve lies in the control points of all n points, right? If this is n points, then this is the convex hull, and the curve lies within the convex hull of this entire set. Okay, So what happens in B spline? B spline, it actually the curve lies between k successive points for convex hull. Okay. What does that mean? K consecutive success or k successive points. Suppose if k equals 2, what does that mean? So the curve has to lie, okay, lie one piece of the curve has to lie between the first 2 points. And then the second piece of the curve has to lie between the next 2 points. And if you keep doing it, so what will be the curve here? So it will keep on. So the curve has to lie. So there is one curve that has to lie within this. There's another piece that has to lie within this. One more piece has to lie within this. So what will be the curve now? Maybe let's go to a simpler case. All of you guys, when I say this is the control polygon. Okay, now this is 1 point, second, third, fourth. The curve has to lie. Okay, one piece of curve has to lie here. Okay, another piece of curve has to lie between the next two. And then one more piece of the curve has to lie between the next two. This is the convex hull for these 2 points. That is k equal to 2 mean. So how the curve will look now? What will be the B spline curve?
So it'll
It
just
is
be
just
the
tracking the polygon itself.
yeah.
So tracking the polygon. Now degree of this guy is what? Between these two, what is the degree?
1.
It's 1. Okay, now between these two, what is the degree? It is 1. And now
Okay.
you have your original. But this is still not true. Okay, we can still mutilate it, go to that Bezier kind of a case, and we'll see that case also. Now we can see that the curve has to lie within k control points, successive manner, taken in a successive manner. What is the successive manner? Now you understood k equals 2k, right? Yes or no?
Yes, sir.
Okay, now go to k equals 3 case in the same thing that we will try a k equals 3 case. Okay, this is fantastic. I never imagined I can use both systems. Okay, now now k equals 3. What is the meaning of k equals 3? That means, okay, if I'll go to a simpler case. So that means if I have 4 points, so what is the k equals 3 mean? Now these first 3 points, there is a convex hull, isn't it?
Yes, sir.
Okay, this is drawing. Okay, you can see this is the convex hull. Okay, so one portion of the curve has to like this. Maybe curve looks like this, possibly. And then the next portion of the curve has to lie within the convex hull of these 3 control points. Okay, this is the convex hull. Remember, there are 2 convexes because k equals 3 successively taken. Now, the next portion of the curve has to lie in the convex hull of the next one. So something like this. Remember, it never goes out of the convex hull of k successive. So you cannot draw a curve like this. I mean, you cannot draw a curve. I don't have any color. Okay. So you cannot draw a curve like this. Why? Because it doesn't lie in the convex hull of k control points. Did you observe? Okay. Now, if we have, let's say 4, what is the now if k equals 4, what is the convex hull?
So it will be equal to the Bezier curve, sir, in this case.
That's what I was fantastic. You already concluded that. So this is the convex hull. Okay, and this curve has to lie entirely within the convex hull. That means it becomes a Bezier curve. So Bezier curve is a special case of your B spline. So when that's happen, what is the relation between k to n?
When
Remember,
k
we are
equals
going.
n, sir.
Yeah, okay, but we are starting from 1 up to n plus 1. So that means k equals
N plus 1.
K equals n plus 1. So when k becomes n plus 1, we'll actually get the Bezier curve. Okay. Now this is what will happen. So now one of the other things that I have to mention is that, okay, in our Bezier curve, usually you take from 0 to 1. T parameters go from 0 to 1. But in this case, this is a piecewise curve. So for that matter, if we have 4 points, and k equals 3, that means there are 2 curves, right? There are 2 curves, one lying within this convex hull and one more. So your parameterization will be like 0 to 1, there is a curve, and then 1 to 2, there will be another curve. Of course, you can normalize this parameterization, but this is what happens. It's not directly from 0 to 1. Of course, if you normalize it, you can make it from 0 to 1. So each piece is kind of computed individually in a sense, okay, and then pieced it together, and it automatically satisfies certain continuity conditions, which we may not go into too much detail. Hopefully all guys are listening, but I'm not getting a
Sir,
feel of it.
Sir, just a quick question regarding this part, as in the
Sure.
multiple convex hulls that are within the, that are created in each case of like multiple
Correct.
case. So,
Correct.
like, how do we like? So it is just like we are creating k convex hulls inside. That is it, or is it like
k consecutive points, not k convex cells. It don't be k convex cells. Like k equals to not just two hulls. K equals means you take the k successive points and then do the convexal of k consecutive points.
okay?
So for example, here is a bigger picture, right? A k equals 3 here and there's no many points. So you can see that this is one convex cell taken from first 3 points, and next 3 points there is another convex cell, and you can see next 3 points, I'll probably use a different color. You can see this is one convex cell and it goes on like that. So the entire set of curves will lie within this convex. So if I draw a curve like this, I can still draw rough Bezier on that, something like that. So but it has to lie within the convex cell of this set of points. Okay.
Yes, sir. So, especially for this such a case, I'm asking like if we are unable to divide it into three like parts like that.
You can always divide. Why? There is no, it's a set of points, you can always divide, right? When you show me a case, see, even if in the collinear case, you can still divide, okay? Suppose if k equals 3 here, okay? The first 3 is one convex cell, correct? Next 3 is
Yes,
another
sir.
convex cell.
Sir,
The
but
curve,
there is one
so we
overlap.
back to the other case. So the curve will be along this, but the degree will be, degree will be 2 here.
Sir, but there's an overlap here, as in.
That's okay. No. But there will always be a starting and thing well defined for that. There won't be any parametric overlap between these two. See, these 3 will account for a curve from, let's say, from here to here. And then when you start from for the other 3, then the curve will again start from here and then go. So there will be some continuity between these 2 pieces. Okay. But this will not overlap between one portion of the curve to other portion. That is why the parametric is very relative. So if it's 0 to 1, then it will be like 1 to 2. It's basically given as less than 1. So it is not exactly equal to also. So it is like 0 to less than 1 and then 1 less than 2. And then last point will actually be equal to 2, which is a special condition on actually. In practice, that is what we do. It's a less than condition, a strict less than is being imposed on. I will show you that equation, but this is the philosophy of a B spline curve. So the idea of a B spline curve is that you can have any number of control points as the input, but I will also have a control over the degree of the curve that I can generate. So did you get this point?
Yes, sir.
Yes, sir.
Okay.
Sir,
If you guys are
I have a doubt that is like that goes from what Vignesh said. Sir, when we have like overlapping of convex hulls between two like convex hulls, in the first convex hull, if we cannot use Bezier in curve within each
no.
convex hull.
It is not individual Beziers unpieced. It is not individual
Yeah,
Bezier.
because when we use
Basis
Bezier,
function is still different. Okay, basis function is different. But I am going to give a philosophical view that it, for example, in this case, okay, let's say I go to this k equal 3k, the curve, one portion will curve like that. Okay, the next portion will start from here and then these 3 on the next. So next portion will be like this. Okay, so there won't be any overlapping portion. Okay, the convex cells also you can see that there is an overlap, and there is, for example, I may not have drawn an exact picture. Okay, so first curve may come from here and then end somewhere here, let us say. Okay, then the second curve will probably start from here and then it will keep on going. Okay, and then the third, this is into the third hull. So then next portion starts and then continue like this. Okay, something like this.
okay, sir.
But you can see that the curves lie within the pieces of the individual convex cell. It won't never
Yes,
come
sir.
out something like this. Okay, that is the idea.
Yes, sir.
Yeah, okay, where you exactly start and where you exactly end, okay, you have to have some computational feel on that. Okay, it is not going to end at one of the edges of the convex cell and then there is overlap region with the other one and then it's not going to start from the previous guy. What I'm trying to say is that if you are doing something like that, it is not going to end exactly here and then the other guy is going to start and then there is a overlapping here. There's no overlap here. This won't happen. Okay, is
Okay,
that
sir.
the convex cell regions can overlap. Okay. But the
Yes,
idea
sir.
is that it is going to lie within the convex hull. That is the idea. Convex hull of k consecutive points. But the curve will not overlap.
Okay, sir. Thank you, sir.
Okay?
So
Yeah.
can we say like this that if you're drawing Bezier of say for 3 points you're taking, so first drawing that Bezier and doing the consecutive Beziers, and when they're intersecting from that point to move on to the next curves.
No, you can't draw Bezier because see why you cannot draw Bezier. For example, if you draw Bezier for the first k control points, okay, what should happen? Then this Bezier itself it should start and end like this. Okay. Okay, that is what Bezier do because Bezier follows the convex hull, and this will never happen in a B spline. Okay, B spline is not going to touch the point directly here. So you cannot piece Beziers. I mean, you can piece Bezier, that's a different problem, but not using the B spline basis function. Okay. So this will be something like this. Okay, and then first core control, then there will be another guy. This always will be like this. There won't be any overlap between that. So we cannot piece Beziers here. So Bezier comes only when you have k equals n plus 1. That means when you have a Bezier, there is only one curve. There are no pieces there. Because that B spline is now reduced to a Bezier, and the parameterization will be from 0 to 1 over. That's all. You'll get a single curve like this.
So
Okay,
then how
so
is it determining that it has now come on to the next zone? It has surpassed the previous zone and it has come to the next
that
zone.
is
Now
what this B spline equation does. Okay. So this is a conceptual feel of what you see in equation. Okay, if you see equation, it will be a little bit bamboozling on that. Let me show the equation there. Okay, so this is basically a picture of varying order. So as you can see that if I have something like this and k equals 2, then you know that by k equals 2 means I have to have curve between first 2 and then next 2 and then the next 2. That means I will get my entire control polygon itself as my, but remember this is a piecewise curve. Okay, if I have k equals 2, that means I have 3 B-spline pieces on that connected with certain kind of continuity. In this case, we know where it is getting connected. In all cases, that need not be the corner point on it. Okay, so but you can see that this is k equals 3 and this is what is the k equals 4 ks?
The Bezier curve, sir.
It's a Bezier curve. Fantastic. Okay, they will come back over to that point. And okay, there are also other things that happen. So you can put multiple vertices, and then like in this case, the number of control points resemble like B1, B2, again B2, you repeat that guy, and then B3, and then B4. So what happens is that in the normal case, this is only B1, B2, B3, B4. Okay, where you add one more point, but repeat the same point again. That is the idea. Now the curve gets pulled towards that control point. You can see the previous case, it was somewhere here. And now if I add the same control point again, it gets pulled towards the control point. Okay, of course, at some point of time, we can make it to pass through that control point in some instances. Okay, so this we cannot achieve using a Bezier. It's very hard to achieve this in a Bezier curve on that. And the another aspect of this B spline is that you will have a local control. So if you can see, this is the original control point. As you move only this control point, you can see the curve that is somewhere here, only local changes are happening. This is the local change. So these segments are all still the same on that. Okay, whereas, so that means you have more local control on the B spline compared to what you had on the Bezier. Remember, if you do it same thing on Bezier, the entire curve may look something like so. Entire curve may get changed. That won't happen in a B spline. So B spline is more local control. It's not completely local. There are some conditions on the local things also, which we won't go into the details. But this is the idea of a B spline. Now, okay, the critical part or the one which is a bamboozling part. And now this is the basis function. Okay, now this is tricky. You can see that this is the fundamental equation. Okay, where the alphas, remember, it's again the entire equation is again sigma. Okay, I don't know whether I missed that. So sigma bi ni plus 1, sorry, ni comma k of t. This is the equation for finding the p of t. So same as your Bezier equation, except that j has been replaced by n comma k. Remember, k is a order. So k can vary from 2 to n plus 1. So now this entire equation gets changed because of bringing on to k as well. Okay, so now, okay, this is difficult to understand the entire part, but this is again a recursive equation because you can see ni comma k will depend on ni comma k minus 1. That means if I have an order k equals 2, it will depend on k equals 1. So this is the base equation of that. So you can see there is a strict less than on the parameter. This is basically range of parameter, and this range of parameter comes from what is called a knot vector. So this is all too much technical on that. So you can see there will be a curve between 0 to 1 and another curve between. These are various type of knot vectors. So we can have more control on the B spline curve by changing these knot vector type, which I think I will not go too much into the detail. Already it's a little bit too much. But the idea of the B spline, you have a hell lot of control on that. Okay, and you should know how to use it. That's a very big point on that. But you can clearly see that we have more control than what we had for a Bezier curve. So then let me just try to see if I have some behavior of these functions. I don't think, okay, I still seem to have something. Okay, so now you can see that for this particular knot vector, you can see that there is a 0 to 1 portion and then 1 to 2 portion. So these two are parametric ranges, 0 to 1 and 1 to 2. So you can see that if you look at this entire set, you can see it is still symmetric. But you can see that there is behavior from 0 to 1 and then there is one more behavior from 1 to 2. But both you can see there is a symmetric behavior on that. Okay. So this is how one of the B-spline basis function. This is called as the open uniform knot vector. I'm not going into the details of it. But then there are other ways of parametrization that are called the periodic uniform parametrization and so on. And the curve will have a little bit change of behavior on that. Okay, but you can see this similar to the your Bezier, but not exactly same. You can see one of the pieces will lie from 0 to 1. The other piece of the curve will lie from 1 to 2. And you can see that here there is a clear-cut division between the graphs that you can see. Okay, but of course it's very difficult to read completely on this. But one thing that you can find here also, what is the K here?
K is 3.
Okay, now if you take your equation, this is B1 N1 comma 3 plus B2 N2 comma 3 plus B3 N3 comma 3, right? Plus B4 N4 comma 3. Because there are 4 control points, N plus 1 equal to 4. This will be the equation of the B spline. Now if you observe from this graph, can you say anything more? Okay, for example, N1 comma 3. N1 comma 3 plays a role till what? Till what parameter?
First convex curve, sir.
So this also explains the first convection. Exactly. So you can see N1 3 is 1. After that it is 0. So it now doesn't even play a role after this. So there is no N1 3. So only this. So I can see that for this half, you have one N1 3, N2 3 and N3 3 playing a role. Okay. Then that B4 has no role to play. See, this also explains the local control better. And after this parameterization 1 to 2, you can see that N13 doesn't play a role at all because N13 has become 0 here. So now you can see these equations, only N23 there is a value, N33 there are some values, and N43 plays a role. So that means the first control point is not going to have any effect on this value of parameterization from 1 to 2. So this clearly explains somewhat the local control of your the B spline curve. I mean, I don't know whether internet was there completely. Was it there?
Yes, sir.
Yes.
Okay. Now you also see the local control or little bit more local control than your B spline and than your Bezier. And this graph or this basis function explains the idea of why some control points will be left out after certain parameterization. So that is why you achieve a better local control in your B spline curve. And I'll also try to show the demo. I think you're closing to the. Hope all guys are listening. I'm really worried. Okay, this is a kind of a graph which talks from N1. This is at a higher level. And then you can see N13 will depend on N12 and N22. And then N23 will depend on N22 and N23 and so on. This is like the dependencies from higher level to a lower level. That is why you see that if after some point of time, only some of these Ni1 functions will play a role. Some will not play a role. And this propagates up. And thereby some of the control points will be left out. Okay, this is a broad idea of this dependency diagram, though it's not a great explanation, but it somewhat explains because you can see that this is the condition that we have to use. And in this condition, you can see that, okay, I'll just go back and come so that all other things are done. So you can see that in this particular condition, there is a strict less than. So it will always be 0 less than or equal to t less than 1, and then 1 less than or equal to less than 2, so that there is not even an overlap between one piece of the curve. It's exactly joins there. Okay. So that is the idea of this putting a less than value, and you can see that ni1 goes to 1 and is 0 for all. Thereby, this dependency diagram will tell that the propagation of the n functions. Okay, it's a little bit difficult to understand everything on this, but this is what happens, and thereby B spline is actually more local control than what you can get in a Bezier curve on that. Okay, so
Sir,
okay, I think maybe
another quick question. So, unlike the Bezier, this B spline is not always differentiable at all points of the curve.
no,
Can that-
differentiability property also have been shown. It is always shown to be some k minus 2 continuous or c power. See, there is something called as G continuity and C continuity. But theoretically, even though it might look like a sharp corner, or it may look like something like this joined from some here and somewhere there, but there are some continuity condition maintained across the local neighborhood here. Okay.
Okay.
Okay, so that is a bit more theoretical, as you said on that, but it is all maintained. So there is some something called a c power k minus 2 continuity is being maintained. So obviously, so when you saw a curve like this, right? Okay, when you saw a curve and if k equals 2, you know that the entire B spline curve is also the control curve. So you can see that there are some sharp points on that. So c power k minus 2 means it's c naught continuity. That means c naught means it is only joined at the points, whereas c1 means the tangents are the same direction, and c2 means curvature continuity. Curvature is also maintained, and so on. Okay, so there is some theoretical understanding of what that continuity will be depending on k. Okay.
Yes.
Yeah, but you can. This is the theory actually. C power k minus 2, as far as I can remember. Okay, so okay, these are all. Okay, you can also make a curve by repeating this parameterization. Like you remember in your original case, if you have a curve like this, a B spline curve may have 3 pieces. One piece maybe something like this. Another piece may come from somewhere, and then one more piece, let's say, from something like this. Okay, so that means these will have a parameterization 0 to 1, 1 to 2, and 2 to 3. Okay, we can also collapse this curve by knocking off this and then repeat to be 1. So your parameterization 0, 1, 1, 3. What will happen that this guy will come down until it will pass through like this. So that is what happens here. So you can see this parameterization repeated. So this is called as a repeated knot value. I mean, obviously B spline is very intricate. So this repeated knot value, you can push the curve to pass through a certain control point, which is also almost impossible to happen in case of Bezier unless they are all collinear. Okay, after that, it never happens in Bezier only. You can never make a Bezier curve to pass through a particular control point, except in the case of a collinear system of control points. You can never do that. Okay, and then this is another control that you can have in B spline curve. Okay, I think these are all little maybe too much. Like for example, what this equation tell is that you can add weights to the control points, and then you can pull the curve towards that control point. You can add hi, let's say h1 equals 100. That means or h2 equals 100. So if you have a control point like this, instead of curve like this, you can push the curve as close to that control, which is again not possible in Bezier. But this is a special case of B spline, or this is a superset called as rational B spline. I mean, rational B spline is the not the topmost. There's one more guy that is the topmost, that is called as so you can see the behavior is rational B spline. When you have one of the thing as 0, this is a flat, and then as you increase the weight for that control point, you can see the curve gets pulled towards that control point. Okay, so if you have high h3 as a very large value, you can push the point very close to that control point. So the point on that curve will be going very close to the control point. This is a rational variety, which is the superset of the previous one.